In this video, we're going to be looking at our first application of the formula Q is equal to mc delta T and also of specific heat capacity, that being thermal equilibrium, which is just a fancy way of describing when the temperature of two different substances that are in contact with each other become equal. This is important in the field of metallurgy and metalworking in general. Whenever you want to form a specific shape with metals, you need to heat that metal first so that it glows like this. At this point, you can hammer it and bend it into a specific shape to form the tool that you want. In order to get that metal to conform to the final shape that you want, it is submerged into a bucket of usually room temperature water in a process that we call quenching. Now, at this point, we can predict what's going to happen to the temperature of both the iron that we're working with and the water. So, obviously, the initial temperature of the iron that you're working with is going to be significantly higher than the temperature of the water, which means when the hot iron is submerged into the water, the iron's temperature is most likely going to decrease, and therefore, if we think about our formula, Q is equal to mc delta T, the change in temperature of the iron is going to be a negative number because you're going from a higher initial temperature to a lower final temperature. Conversely, if we consider the water that we use to quench the metal we're working with, water's temperature is going to be lower than the initial temperature of the metal, which means that water's temperature is most likely going to increase when a hot metal is submerged into it, and therefore its delta T term is going to be greater than zero because, again, we're increasing the temperature. This realization is going to have very important consequences in how we set up a thermal equilibrium equation. So if we consider this situation here, what we want to calculate is the final temperature of both the water and the iron, which will be the same because of thermal equilibrium, after the iron is submerged into the water. And again, we can set this up as an equation where each side is the Q is equal to mc delta T formula, but on one side we have iron, and on the other side we have water. So if we set up iron on this side, we start with the mass of iron, which is, in this case, 40 grams, which we multiply by the specific heat capacity of iron, 0.449 joules per gram per degree Kelvin, and we can see that grams cancel here, so all we need is the change in temperature. Now, the problem here is that we don't know what our final temperature is going to be, so we're going to say that the variable x is equal to our final temperature after thermal equilibrium is reached. So x is the final temperature, and if we want delta T, we can subtract the initial temperature of the iron here, which is going to be 80 degrees Celsius. Now, this is where it's important to consider whether the temperature of the iron is going to increase or decrease. Now, since iron's temperature is going to be decreasing from initial to final, that means that this number here is going to be negative. And this is very important here to consider because when we write the other side of the equation, this direction is going to be very important. Next, we set up the Q is equal to mc delta T for our water here. So the bucket of water has 100 grams of water, which we can multiply by water's specific heat capacity, 4.184 joules per gram of water per degree Celsius in temperature change. Again, grams cancel, so all that we have left to consider is the change in temperature. Again, we don't know what our final temperature is going to be, so we're going to leave this term as x, and we're going to subtract from that our initial temperature, which is 25 degrees Celsius, and from there, all that we need to do is expand each side of this equation out in order to solve for x. Again, take note, because the iron's temperature is going to be decreasing and the water's temperature is going to be increasing, make sure that we have a negative sign to indicate that this change in temperature is a decrease, and that there is an implied positive sign here to imply that water's temperature is going to increase. If we expand all of this out, including the negative sign, what we should see is that we get negative 17.96x plus 1436.8 on our iron side. And if we expand this out here, again, 100 times 4.184 becomes 418.4 times x minus 10,460. And then from here, it becomes a simple matter of isolating all of our x terms on one side and all of our constant terms on the other side. So again, we're going to, when we want to move this over, we're going to add 10,460 to both sides. So we can do that, plus 10,460 plus 36.8, and when we add 10,460 to this side, it cancels out. And because this number with our x term is negative, we can add 17.96x to both sides. So when we do that, we would have 418.4x plus 17.96. And in the next term, once we have what coefficient we have in front of x, we can isolate x by dividing both sides by each other. And if we do that, if we add both of these numbers up, when we isolate x, we would end up with 11,896.8 divided by 436.36. And what we would get here after we divide these is what the initial temperature is going to be. And if you put this into your calculator, you should get that x comes to approximately 27.2637272 degrees Celsius. Again, we need to consider significant digits, so we see the smallest number of significant digits in our in our situation was 2 from 25, so we can round x to 2 significant digits and say that our final temperature is approximately 27 degrees Celsius. If we check from the situation, again, assuming that the iron temperature is going to drop when it's quenched in water, which means that the heat from the iron is going to move from the iron into the water, causing water's temperature to change. But because water has such a high specific heat capacity, the change is not significant compared to the decrease in iron's temperature. So this is useful as an application of specific heat capacity because it allows us to predict the amount of water that we would need in order to quench a specific metal that we're working with and anticipate what the final temperature of the water is in order to control the metal shaping as best as possible. A second application of Q equals mc delta T is to determine the specific heat capacity of a substance that we don't yet know. So in this situation, again, we're taking a certain mass of nickel and with a higher temperature than water and quenching it in water. And what we can do based on calculating what the final temperature is going to be, we can find what the specific heat capacity of nickel is, even if we don't know it. So we would set this question up the same way as a thermal equilibrium question, starting with 100 grams of nickel. Let's preserve the significant digits and write 100.0 grams of nickel, and we're going to multiply this by the specific heat capacity, C of nickel, which we don't know, so this is our variable, and then we're going to multiply this by the change in temperature. So in the case of nickel, we know that the final temperature is 26.3 degrees Celsius, and we're going to subtract from that 150.0 degrees Celsius, and there's our setup for the specific heat capacity of nickel. And on the other side, we would do the same for water. We see that we have 1 liter of water. Again, specific heat capacity is based on grams, so we can quickly convert this if we assume that 1 gram of water is the mass of approximately 1 milliliter of water. We can do this conversion quickly. So 1 liter is equal to 1,000 milliliters. And if we assume that 1 gram is the mass of the approximate mass of 1 milliliter of water, that means that we're dealing with 1,000 grams of water. We know the specific heat capacity of water, 4.184 grams 4.184 joules per gram of water per degree Kelvin that we increase. And we know that the change in temperature is going to be final temperature 26.3 degrees, initial temperature is 25 degrees yet again. And all that we need to do is solve for the specific heat capacity of nickel, which means that if we divide both sides by 100 grams and by the temperature change that occurs with nickel, then we can figure out what the specific heat capacity of nickel is. So I'm going to do that here. So in the numerator, we have, again, 1,000 grams of water times 4.184 joules per gram per degree Kelvin. And if you do 26.3 minus 25, that comes to 1.3 degrees Kelvin. And there is our numerator. And in our denominator, we would be dividing by 100.0 grams times this number here, which you'll notice that the sign is not quite right. Now, obviously, it doesn't make sense that our specific heat capacity would be negative. Specific heat capacity is always going to be a positive number because it can only measure magnitude and not direction. So I've simply written out the difference between 150 degrees Celsius and 26.3, and it comes out to 123.7 degrees Kelvin that we have changed. And if we look at our units, we see we have joules in the numerator and grams and degrees Kelvin in the denominator, and that means that we have done the conversion to find specific heat capacity correctly. So all that remains is to put this into your calculator, and if you do that, that number comes to approximately 0.43970, which again, we see our measurements only have 2 significant digits, so we can round this to approximately 0.44 joules per gram of nickel per degree Kelvin of temperature change. In the next video, we're going to look at a different application of Q is equal to MC delta T used in order to determine how much energy a reaction consumes or how much energy a chemical reaction produces.